In this lesson, we're looking at projectile motion, which is the 2D version of uniform accelerated motion. So let's start with a review of 1D uniform accelerated motion. When an object moves with constant velocity, as shown by this graph, we call this uniform motion. The velocity is constant and the graph is horizontal. Accelerated motion means that the velocity is changing. For accelerated motion, the graph will not be a horizontal line. The initial and the final velocity will be different. We define the acceleration by the equation final velocity minus initial velocity divided by time. This is the rate at which the velocity is changing. In math class, you would call this the slope of the graph. The denominator, the delta t, that represents the run of the graph. The numerator, the final velocity minus the initial velocity, that's the rise of the graph. And when we divide rise divided by run, that gives us the slope of the graph. Uniform accelerated motion means motion with constant acceleration. We can recognize that from the graph because if the acceleration is constant, the slope must be constant, so the graph must be a straight line. If the graph is curved, that means the acceleration is not constant. Sometimes you may see a graph that's made up of two or more straight sections. In that case, you can treat each of the individual sections as uniform accelerated motion. Another thing we learned about uniform accelerated motion is that the area between the time axis and the line on the graph, that represents the displacement of the object during that time interval. When the motion is uniform, the time represents the base of the rectangle, the velocity represents the height of the rectangle, and when we multiply them together, base times height, to get the area of the rectangle, velocity times time, that tells us the displacement. Accelerated motion, delta t still describes the base, however the height is not constant. In order to get the correct area, we have to use the midpoint of the line, which is the average velocity. For uniform accelerated motion, we have a second equation, which states that we can calculate the displacement by averaging the initial and the final velocity and then multiplying by the time. Let's do an example of a 1D uniform accelerated motion problem. A soccer player kicks a ball straight up from the ground. The ball rises 15 meters before it starts to fall back to the ground. What was the soccer ball's velocity when leaving the player's foot? Now, if we look at our two equations, we can see that there are 5 variables in total. We've got the acceleration, we've got the initial and the final velocity, we've got the displacement, and we've got the time. So what we can do is we can make kind of a table. We can list the 5 variables that we're interested in solving for. Now, this is one-dimensional motion because the ball is being kicked straight up. It's going to move straight up and then straight down, so it's only going to have a y component. There's no x motion that we need to be concerned with. We'll start by filling in the information that's given in the question into the table. So we're told that the ball rises 15 meters before it starts to fall back to the ground. So if we take the ground as the origin, that's our initial position for the ball. The final position for the ball is 15 meters above the ground. That tells us that the displacement vector would be positive 15.0 meters. That still leaves us with 4 other quantities that are not given in the question. We've only got 2 equations, and so that means we can solve for at most 2 unknowns. So before we can continue to solve the problem, we're going to need to find some more information. We need to have at least 3 of these 5 variables before we can solve for the unknowns. If we're neglecting the effects of air resistance, we can assume that the acceleration will be negative 9.81 meters per second squared. This is because once the ball leaves the soccer player's foot, gravity is the only force causing it to accelerate, and we know that on Earth, the acceleration due to gravity is always going to be negative 9.81. The third thing we know is going to be the final velocity. Let me adjust the velocity graph here. We're going to start with a positive initial velocity. The ball is going to rise. As the ball rises, gravity causes it to slow down. Once it reaches its highest point, it's going to begin to fall back to the ground, which tells us that the velocity is going to eventually become negative. So we've got a velocity graph which starts on the positive side and eventually crosses the axis and ends up at the negative side. This part of the graph here, above the time axis, that represents the upward motion. Once we cross the time axis, this part below the graph, that represents the downward motion. The highest point in the motion occurs right where the graph crosses the axis. Essentially, when the ball's moving upward, it's got to have a positive velocity. Once the ball starts to fall, it's going to have a negative velocity. The point at which the velocity changes from positive to negative, that's where the velocity is 0. That's going to be the highest point. The third piece of information that we can record in our table is the fact that the final velocity is 0. Because we're only looking at the upward part of the motion, we're starting with an initial velocity that's positive but unknown. We're not told how fast the soccer ball's moving when it leaves the soccer player's foot. That's what we're trying to find. Now that we've got 3 known quantities, we can use the 2 equations to solve for the 2 that are missing. What we'd like to do is to find an equation that only has 1 unknown. And unfortunately, that's not the case here. The 2 unknowns are the initial velocity and the time. If we look at the first equation, we can see that both unknowns appear in that equation. If we look at the second equation, we can see again both unknowns appear in that equation too. So what we do when we have 2 unknowns and we have 2 equations and both unknowns appear in both equations is we have to solve the system by eliminating one of the 2 unknowns. What we can do is we can take the first equation and we can algebraically rearrange it to isolate delta t. So my first step, I'm going to move the delta t to the left side by multiplying both sides of the equation by delta t. Then to isolate the time, I'm going to divide both sides of the equation by the acceleration. Now I've isolated the delta t, I can substitute that into the second equation and then use the result to solve for the first unknown, which is going to be the initial velocity. Now fortunately, you don't have to do this algebra yourself. The rearrangement that we get when we combine the 2 equations, that's actually listed on our formula sheets. So the equation we obtain when we eliminate the time looks like this. It's v final squared is going to equal v initial squared plus 2 times the acceleration times the displacement. You'll notice that most of the time I indicate vectors by putting an arrow on top of the symbol. That's not the case with the initial and the final velocity here, and the reason for that is because both velocities are squared in the equation. So by squaring them, it doesn't really matter whether the velocity is positive or negative. Squaring always produces a positive number. So in this equation, the directions of the velocities don't matter. That's important to keep in mind because when we're solving for v initial or v final using this equation, the equation will not tell us whether the direction should be positive or negative. Now we obtain this equation by combining the first 2 equations to eliminate the delta t. There are actually 2 other ways we could have combined the equations. We could have eliminated the v final instead because it appears in both equations, or we could have eliminated the v initial, which also appears in both equations. So that means there are 2 other ways in which we could have combined our original equations, and those 2 equations are also listed on your formula sheet. So when we're solving uniform accelerated motion problems, essentially what we want to do is we want to go through our list of 5 equations and we want to pick out an equation that only contains 1 unknown. And we should go through the equations in order. The reason that's best is because the earlier equations tend to be simpler. As we go through the list, the equations further down tend to be more complicated, and we'd always prefer using a simpler equation rather than a complicated one if we can. So in this problem, the first 2 equations contain both unknowns. They're not going to help us to begin with. So we're going to start with the third equation because it only contains 1 unknown, which is the initial velocity. So we're going to algebraically rearrange this equation. The first thing I'm going to do if I'm trying to isolate the initial velocity, I'm going to subtract 2a delta d from both sides, and that will isolate the vi squared. And then I'm going to need to take the square root of both sides, and that will give me v initial. And as I said a moment ago, remember, when we square root, the answer can be either positive or negative. The equation doesn't tell us which is the correct sign. We have to tell from the context of the problem. So in this example, since the soccer player is kicking the ball upwards, we know that the positive answer is going to be the correct one. Now we can get out our calculators and we can type the values into the equation here. So the final velocity is 0, the acceleration is negative 9.81, the displacement is positive 15.0. If we type that in on our calculator, we get 17.2. That's going to be the initial velocity. And as we said, because the soccer ball is being kicked up, we want to make it positive 17.2. Now there's only one unknown remaining. So we can use any of the equations except for the one that we've already used. It's simplest to use the first equation. And in fact, we've already done the algebra. We've rearranged it to isolate the delta t. So all we have to do now is to plug the numbers into the formula. So if we type that in our calculators, enter 0 for the final velocity, the initial velocity, that's the 17.155 that we just calculated. The acceleration is negative 9.81. That gives us 1.75 seconds for the time. Now that we've solved for all the variables, we can make a more accurate graph. The initial velocity is 17.2, and the final velocity of 0 occurs after 1.75 seconds. All the numbers in our table represent something about the graph. The 1.75 seconds, that represents the base or the run of the graph. That tells us how far apart the initial and final points are in time. The initial and the final velocity tell us where to plot the 2 points to mark the beginning and the end of the motion. The slope of the graph, that's the negative 9.81, that's the acceleration. And the area of the graph, that's the positive 15.0, which represents the upward displacement. We can also draw a graph of the ball's position as a function of time. We know that it starts on the ground at a position of 0. We know that after 1.75 seconds, it's reached a position of 15.0 meters. However, the position versus time graph will not be a straight line. Because the motion's accelerated, that means the velocity, in this case, is decreasing. It starts with a fairly big velocity of 17.2. So what that means is, at time of 0, the graph has an instantaneous slope of 17.2. And as time proceeds, because gravity is slowing the ball down, the slope of the graph gets less and less steep, and eventually at 1.75 seconds, the highest point in the motion, the slope of the graph will be 0, corresponding to the final velocity. So for the displacement graph, we don't get a straight line, we get a curve. And the shape of this curve is in fact a parabola. Now that we've reminded ourselves how to solve uniform accelerated motion problems in one dimension, let's now look at a two-dimensional situation. Suppose we're given a question where we're asked to find the range and the hang time when the player kicks the ball with a velocity of 20.0 meters per second at a 60.0 degree angle. The ball lands on the ground 3.00 meters lower than where it was kicked. So we've illustrated what's going on here. The soccer player is going to kick the ball. The initial velocity is going to have a direction of 60 degrees. It's going to follow an arc, and we'll learn later that the arc is actually parabola shaped. And then it's going to land on the ground. Point of landing, according to the question, is 3.00 meters lower than where it was kicked. Since I've drawn the x-axis along the ground where the ball is landing, I've put the initial position of the ball 3 meters above the ground. Now, when the question asks us to find the range and the hang time, for the range, they're asking how far the ball travels horizontally, so how far it lands from where it was originally kicked. The hang time is the total amount of time that the ball is in the air as a projectile. Now, what makes this question two-dimensional is the fact that there's motion in both the x and the y directions. I've already drawn in the initial velocity vector. If I draw in the remaining vectors, the final velocity when the ball lands on the ground is pointed down and forward. The acceleration, just like in 1D, the acceleration is caused by gravity, so it's going to be directed straight down in the negative y direction. And the displacement, we can illustrate that as an arrow starting from the ball's initial position and ending at the ball's final position. And you can clearly see from the diagram that most of these vectors have both x and y components. As we've learned in the last few lessons, the way we approach 2D problems is by separating all the vectors out into x and y components and by solving the x and the y parts of the motion separately. So just like we did for our 1D example, I'm going to make a table. I'm going to label my 5 variables. So I've got my 4 vectors, acceleration, initial and final velocity, and displacement. And I've got the time, which is not a vector, it's just a scalar. But this time I'm going to have 2 columns, 2 additional columns. I'm going to label them x and y because I have to include both x and y components. Let's start by filling in what we know. We're neglecting air resistance, and therefore the acceleration is just the acceleration due to gravity. And since gravity points straight down, that means the x component of the acceleration is going to be 0. The acceleration vector has no x component, and the y component is going to be negative 9.81 meters per second squared. Because time is a scalar, it does not have a separate x and y component, it's just a single number. So these two cells for the time have been joined together to indicate that they're not separate. I've also joined the initial and the final velocity for the x component. The reason for that is because the x acceleration is 0. Remember that what acceleration means is the rate at which the velocity is changing. To have an acceleration of 0 means that the velocity is not changing, which is just another way of saying that the initial and the final velocity are the same. So I've joined these two cells of the table into one to indicate that those two velocities are in fact the same value. Now we were given the initial velocity of the soccer ball. It's 20.0 meters per second. It's at a 60.0 degree angle. That's the polar form of the vector. We need to calculate the components, the Cartesian form of the vector. We need to know the x and the y components. So as we learned earlier in this chapter, we're going to use the sine and the cosine formulas in order to calculate the x and the y components. So I'm going to get out my calculator. I'm going to type in 20.0 times the cosine of 60.0. So 20 is the magnitude, 60 is the direction. The cosine equation gives us the x component. So the calculator is telling me that the x component, the forward motion of that initial velocity, is 10 meters per second. So I can fill that in my table as part of the x component. Then I can do the same thing for the y component. I'm going to use sine instead of cosine. So 20.0 times the sine of 60, and that gives me 17.3, which is the initial y component of the velocity. Now if we look at the final velocity, the x component, as we've already argued, the x component is the same as for the initial velocity. It's still positive 10. The final velocity, I can tell that's going to be negative because the ball is returning to the ground, but I don't know what that component is. Moving on to the displacement vector, the x component is unknown. The x component, that's the range, that's one of the things that we've been asked to find. The y component, however, we do know that. We know that the soccer ball starts 3 meters above the ground, it returns to the ground. That tells me that the y component of the displacement is going to be negative 3.00 meters. Now once I filled in the table with everything that I know, now I can look at my list of 5 uniform accelerated motion equations. The fact that this is a 2D problem doesn't change the equations that we're going to be using. They're the same 5 equations that we use for one-dimensional motion. Now there's not enough information yet to solve the x part of the motion. Although there are only 2 unknowns left, the time and the displacement, when we argued that the final velocity was equal to the initial velocity, we were effectively already using one of these equations. The fact that the acceleration here is 0 is what tells us that the initial and the final velocity are equal. So because I've already used one of my equations, I can only solve for one remaining unknown. So we're going to have to start with the y motion. The 2 unknowns are the final velocity and the time. So as with 1D motion, we're going to go through our list of equations in order. Any equation that has both time and final velocity in it is not going to work. So we're going to pick the equation, the first equation that we find that only has one unknown in it is the third equation. To solve for the final velocity, we need to square root both sides of the equation. Remember that when we take the square root, the answer can be either positive or negative. The equation isn't going to tell us which one, but we can see from our diagram that the final velocity is going to be negative because we were told that the ball is kicked up and that it later returns to the ground. It has to have a downward or negative velocity when it lands on the ground. So if we get out our calculator, we can type in for the initial velocity, we're going to type in 17.3 because this is the y motion that we're solving for. For the acceleration and the displacement, we're going to use negative 9.81 and negative 3. And the calculator gives us 18.9 for the answer, and we're going to take the answer to be negative 18.9. That leaves us with just the time as an unknown for the y motion. So we're going to go back to the first equation. We're going to rearrange it. So first of all, multiply both sides by the time so that the time is no longer in the denominator. And then to get the time by itself, we're going to divide both sides by the acceleration. And then we can type those numbers into our calculator. So the final velocity, that's going to be the negative of what we just calculated, negative 18.9. We're going to subtract the initial velocity, divide by the acceleration, and the calculator gives us 3.70 for the time. So now we've completely solved for the y motion. There are no longer any unknowns. So now let's go back and look at the x motion again. The only unknown is the displacement. So the first equation that has displacement in it is equation number 2, which says displacement is equal to the average of the initial and the final velocity times time. So vi plus vf over 2, that expression is averaging the velocities. But in the case of the x motion, because there's no acceleration, the initial and final velocities are the same. So we don't really need to average it. The average of 10 and 10 is just going to be 10. So to get the displacement, we're going to take our average velocity, which is 10. We're going to multiply by the time, which is 3.7. And you probably can do that even without a calculator. That's going to be 37.0. Now the table's completely filled in. There are no more unknowns. So we have solved for the motion. Now let's go back and see what the question was actually asking. They want us to find the range of the motion. They want us to say how far away the ball landed horizontally from where it was kicked. So that's 37 meters. That's what the calculations are telling us. The second thing the question asked for was the hang time, and we calculated that the soccer ball spent 3.70 seconds as a projectile from the time it left the player's foot until the time it made contact with the ground. Now, sometimes the question will ask you for an answer in polar form. So, for example, the displacement vector, we know that it has an x component of positive 37 and a y component of negative 3. If we had been asked to express that in polar form, we could use the Pythagoras formula to calculate the magnitude, and we could use the inverse tangent formula to calculate the direction. Similarly, we could do the same thing for the final velocity. If I wanted to know the magnitude of this velocity and the angle at which it's landing, I could take the positive 10 and the negative 18.9, those are my x and my y components. I could then use the Pythagoras formula to determine the magnitude of the vector, and I could use the inverse tangent formula to determine the direction. Suppose we had been asked to find out how high the ball rises before it begins to fall back to the ground. If we look back through our table, some of the information will remain the same, but some of it's going to have to be changed. The acceleration is still caused by gravity, so it would remain unchanged. The player is still kicking the ball with a speed of 20.0 meters per second and a direction of 60.0 degrees, so the initial velocity would remain the same as well. The final velocity, however, would be different. When we did the 1D example a few minutes ago, we said that the highest point in the motion is where the velocity changes from positive to negative, so at that particular instant, the velocity would be 0. That's still true for the y component of the velocity. Up and down refer only to the y motion. So the final y velocity here would still be 0. The x velocity would not be 0. We argued before that because the acceleration is 0, the x velocity has to remain constant. So at the highest point, the x component of the velocity is still going to be positive 10. The displacement is also going to be different since we're only looking at the upward portion of the motion, not the downward portion of the motion. And of course the time is going to be less if we're only looking at a portion of the motion. Sometimes people assume that the time for the upward motion would be the same as the time for the downward motion. This is only true if the ball lands at the same height that it started from. In this example, the upward motion is 3 meters less than the downward motion, which means that the upward motion is going to take less time and the downward motion will take more time. Once we filled in our table with all the information that we know, we're going to get our list of equations and we're going to go through and we're going to look for an equation that only contains one unknown. So solving the y motion first, we can see that the first equation actually will work this time. The only unknown in the first equation is the time. So we can get our calculator, we can plug in the numbers to the equation, use 0 for the final velocity, 17.3 for the initial velocity, and negative 9.81 for the acceleration, and that will give us the time of 1.77 seconds. Now we can use the second equation to calculate the y displacement. So the initial velocity again is 17.3, the final velocity is 0, the time is 1.77 seconds. So plugging those numbers into the second uniform accelerated motion equation gives us positive 15.3 for the displacement. Now remember that the soccer ball starts 3 meters above the ground. So if the question had asked us what's the final height of the soccer ball, it would actually be 18.3. It starts 3 meters above the ground. It rises 15.3 meters from there to a height of 18.3 before it begins falling back to the ground. Now that our y calculations are complete, let's go to the x column. The only unknown here is the displacement, and just like the previous example, the displacement is going to be the average velocity multiplied by the time. The average velocity is 10, the time is 1.77, so the x displacement is going to be 17.7 meters. Now I mentioned earlier that the shape of the trajectory that the ball follows, that's going to be a parabola. The reason it's a parabola, if you look at the fourth equation here, the reason it's a parabola is because this equation is quadratic. That concludes the lesson on projectile motion. Stay tuned for some summary notes.